Let's talk about the palindrome linked list. So you're given the head of the single linked list. So return true if it's a palindrome. So this is an example, and then there are a couple ways to solve these questions. And the easy way is using the recursion. So you will just find out the last node in the linked list. Then you have a pointer here, and then you have a pointer here, and then you will just keep comparing each other. And since this is a recursion pointer, you will this will get recursively back. So you will recursively back to this pointer, and then you will just have to move on the next pointer to compare. So this will be the solution, and this is supposed to be the easy one. And the next one is going to be breadth search. So this is the second solution. So you can actually create a stack, and then I have a fast and slow pointer. So fast moving twice node at a time. So slow pointer moving one this node at a time. So you will actually find out where did you start on your uh, right side of the palindrome linked list, right? Then you can actually, I mean, when you traversing on your slow, you have to push into the stack, and then when you know this is the right side of your pointer, and then you can actually pop your list node value from the stack, and then to compare the current list node, and if they are the same, then you will pop and then you will move on. And this has a trick. This is because so the trick is because if the list node is actually what, okay, if the linked list is actually odd, like this one is odd length, right? This is even length, right? So how do you know this is odd, this is even, right? So when we traverse the linked list based on the slow and fast, we can actually determine is this linked list of odd length or even length just based on this, right? So fast pointer move twice at a time, slow pointer move one at a time. And then when you want to move your fast again, you need to check the condition if the fast is not null, and also if the fast on next is not null, right? You need to check these two conditions. If they are satisfied, then you can move on, right? If they are not satisfied, this is going to be off then, right? So the slow pointer has to move one again. This is because the right side of the linked list does not start at this pointer. So it started at this linked list, list node, be honest. So you are still started from the beginning and comparing with this value based on the stack. And this is pretty much the solution. So let's talk about the recursion first. So I'm gonna say recursion. So I need to create a list node. I'm gonna call L, right? So L represents the head. So I will point at the head, and I need to call the helper function. I'm gonna call traverse and list node. I'm going to call R. This will be my right pointer for my rest of the linked list, right? So traverse, and I need to say head. I need to pass in the head no matter what, right? So if R is actually equal to null, right? If it hit the end, you will return true. All right. So I need a variable to actually store the current value for the right pointer. So I'm going to call result, and then this will be traverse my r.next. So this will just traversing the entire list node to the end, and then recursively back, right? So this will be pretty much nothing, but it will just know where is the pointer at, and then I'll just have to keep updating my result with the current right value and then that value, since they are recursively back, right? So r dot value is equal to L dot value if they are equal. So the reason why I'm using n, this is because I need to keep track of the previous record, and this will be pretty much like no, is this the linked list is a palindrome now, right? So if they are the same, I need to move on my left pointer dot next, right? because a right pointer will recursively back, right? So they are going to be the same. So L will be L.next. And then at the end, I will just have to return the result, right? And this will be the solution. All right, let's submit. All right, here we go. So basically, they are super straightforward. The time is going to be all of n, and the space is constant, right? You are not allocating any space. And let's talk about another solution. So another solution is stack. So I need a stack, right? So what I need to put is put in the, you can put this node, doesn't matter, but they are the same. I'm going to put stack. So I need a fast and slow pointer. So fast equal to head, slow equal to head as well. So well, fast is nano, and also fast.next is nano. So slow equal to slow.next, fast equal to fast.next.next. You need to move twice at a time, right? So if fast is nano, this will actually determine the length is R, right? So I need to move my slow by 1. Alright, now I need to just keep comparing, right? So comparing my slow pointer with the stack, right? So I know where I start from my right side of the linked list. So well, slow is unknown. Slow equal to slow.next. But before I move, I need to check if slow.val is actually not it's actually equal to the stack of pop, right? If they are not equal, I will have to return false. And I just realized I didn't add the value into my stack. I made a mistake last time. So it's actually stack.add, right? So it's going to be slow.val, right? And at the end, if the value is actually success, then you actually have to return true, because you will return false if they are not the same. So this is the solution. And let me submit. Alright, so let's talk about time and space. For this one, the space is all of n. The time is actually all of n as well. Like you have to traverse every single linked list, right? List node in a linked list, right? So this is all of n. The space is all of n is because you have to basically store half of the list node into the stack. So n over 2 is approximately all of n. So this is pretty much it, and I will see you next time. Bye.